Okay, good morning, everyone. I'm Nick. I'm a researcher at the University of Surrey, and I'll be talking about mineshafts and how we can use closed-loop systems. This is very much a kind of preliminary and early-stage work. But first, I just want to say it's just been really great being here and just seeing all the different facets and work that's been done in this field by this community. So thanks for having me. Right, so for the work I'm presenting, I kind of chose a case study just to kind of base the work on. If you're familiar with the UK, you might recognize that as the outline for Derbyshire. And somewhere here, we have Criswell. And Criswell had a colliery operating until 91. And as part of that, there were 2 shafts. And one of those is what I'm using as part of kind of this work. But to do this, we need data, and thankfully, the Coal Authority has a really great tool online, being able to get information such as temperatures, kind of buildings around to identify where heat could go to, and also kind of the points that they're monitoring and data they have and they can license out. Additionally, BGS has another great tool in terms of the GeoIndex and having borehole logs. The shafts that I'm working with did have kind of detailed borehole logs available, and using those, I was able to kind of identify and approximate this geometry for the shaft, which looks a little bit like this. It goes down to about just over 400 meters, and have these 2 seams that intersect at about 200 and 300 meters. And I included this kind of short video. I'm not going to play it all. So I don't know if we can play it, but I thought this was really a good way to visualize and see what a shaft even looks like. And so this is from the Coal Authority. It's online, so anyone, especially watching online, have a look. But I don't have time to play through it. Right. The other kind of piece of input data that's relevant here is identifying a suitable load. So kind of what kind of heating we're providing. I used this kind of study that was a UK-wide study to identify heating loads. And using the data that they published, I kind of identified a load profile that looks a little bit like this with a peak of about 100 kilowatts. So, using shafts, David Banks et al. Had, I really like this schematic, showing different ways you can use a shaft, like open loop systems, closed loop systems, or standing columns. You won't be surprised to hear that we're focusing on closed loop systems for this, even though I know there's a lot of kind of published research and work that has calculated that open loop systems are more efficient. I mean, in general, they're more efficient. They can provide higher loads. But I think there's still kind of room to investigate this, given that closed loop systems don't directly interact with mine water, and therefore they might be kind of an easier sell, especially for pilot projects, or to kind of talk to stakeholders. So the modeling for the shaft, I'm not going to go into too much details because of time, but essentially, so I'm using a software called COMSOL Multiphysics to cover all the physics together. So we have basically heat transfer and heat balance equations. We got fluid flow equations for where we have for the flooded parts of the shaft. And then we have our pipes, which include the flow within the pipes and heat transfer that is coupled. And they look a little bit like this. So they're modeled as 1D elements, and we have kind of input and inflow and outflow in the pipes. Now, one thing that is kind of important in this kind of modeling, this kind of research, is looking at natural convection, and that's the effect where essentially when we're changing the temperature of the water, there's going to be movement because of changes in density. So hotter water moves up, colder water moves down, and that essentially causes some like a circulation within the shaft. Now, I think there's quite a few modelers here, and I think people would agree that modeling fluid flow, especially at kind of this scale and resolution, is very computationally expensive. So I wanted a way to avoid that in order to do kind of a larger scale or larger parametric kind of analysis. And so to approximate these effects, without actually modeling them, I kind of resulted in using a kind of artificially enhanced or convectively enhanced thermal conductivity for the water. So essentially, the idea here is that by increasing the conductivity, you're accounting for these mixing effects by allowing heat to transfer easier. And you do that, the gear to turn to do this is the Nusselt number, which is the ratio of total heat transfer over conductive heat transfer. So essentially, the higher Nusselt number you kind of use, the more you account for the convective effects taking place. And I did kind of a bit of an analysis to see where the range is, what could be feasible here. So by modeling all the different physics, including the natural convection, we get the kind of blue line down there. And then by using different Nusselt numbers, we can say that the higher you go, the closer you get to the fully coupled model. Now, in saying that, because this is an approximation, and again, this is kind of early stage work, a lot of what I'm presenting in the following slides is using kind of Nusselt numbers from the lower side, just for conservatism. So the results will be quite conservative. Right. So this is kind of some example results. This is kind of what the temperature in the pipes looks like, which is something that is kind of key in determining what kind of system you can use. What is interesting to me here is that the temperature fluctuations of the carrier fluid in the pipes kind of stabilizes after the first couple of years, which is good for kind of long-term sustainability. And this is kind of a visual of the temperature fluctuations in the XZ kind of plane. Now, when we're looking at the fluid temperatures, typically when you look at closed-loop systems, you want the temperature of the carrier fluid to be within a certain range, such that it aligns with the operating temperatures of the heat pump. And that, though the ground source heat pumps can operate roughly from kind of -5 or so up to kind of 40 something. Again, for conservatism, I added kind of an artificial lower limit here at 2.5 degrees in order to kind of look at the analysis. Here we're also seeing the YZ direction, which essentially shows the flowing the seams and how that kind of carries the change in temperature downstream. Right. So given the uncertainties kind of around this work, and I wanted to start with a sensitivity analysis to kind of identify for different parameters that we have, different uncertainties that exist, what are their impact on the outputs. So I used the Moore's method to kind of perform an initial sensitivity and identified. So in the graph on the right, on the higher up and further to the right, the parameter is, the more impact it has. So I've identified the flow rate in the pipes and the diameter as being crucial in terms of performance. So I started looking at that kind of parametrically. And essentially what we have is the higher flow rate you use in your pipes, the kind of higher load you can provide, but at the same time, your pumping costs will also increase. So putting kind of the two together and using a bit of a kind of an artificial metric in terms of value, I estimated that there's essentially an optimum point of flow rate that will provide you kind of the highest value of heat given the pumping costs that are affected. Similarly, with looking at the pipe diameters and kind of using kind of the reasonable ranges, going higher diameter, everything else being the same, you can flatten out your load, but you also flatten out your costs. And therefore, when you combine the two kind of together, there is also show that higher diameters of pipes are still kind of more valuable. Another thing I wanted to look at was the kind of how many loops can we fit within the shaft. And essentially what I'm doing here is distributing the same amount of load to different numbers of loops. So it's unsurprising that with less loops, the temperature responses are more extreme because each of the loops is trying to provide more energy. And what essentially happens is, as you increase the number of loops, you can increase the amount of load you can provide, but it does have a marginal gains as you go higher and higher. And therefore, the peak load per loop decreases as you add more and more. So kind of using a lot of the kind of results from different parametric analysis and being kind of less conservative in terms of how natural convection effects take place, I've kind of estimated that for this particular example, and using the heating load that I showed earlier, about 170 kilowatts of peak load could be provided relatively comfortably. The last thing I wanted to do was look at combinations of load, because it makes sense when you have both heating and cooling, they can interact kind of beneficially together. So in this kind of example, I'm distributing the kind of total load instead of 8 loops as earlier to 8. And then for the remaining 2 loops, I'm using an artificial cooling load, which is of 5 kilowatts, which could be typical for a data center will be ideal, or even to provide load to a hospital or something like that. And what's interesting to see here is how those interact together, because you're essentially kind of circulating hot water to some and colder water to others, and there's synergies. And by comparison, for kind of the same equivalent example, if you just use heating and distribute it to all 8 loops, that performs worse. So by providing heating and cooling, you're essentially providing more energy overall, and you get better performance. I'm going to skip over the conclusions because of time, but essentially what I've been talking about, and I'm going to leave it at that. Thanks for your time.